But yeah, good morning, good evening, good night for wherever anyone is. And so yeah, I'm Robbie. I am an assistant professor at Columbia University, and yeah, so just as a brief summary, yeah, I mean, largely I focus a lot on climate change, equity, and I've got a lot of focus on the United States work, but also want to show some kind of global stuff that I've been working on as well. This is the lab, and so yeah, I sort of will showcase previous recent work, but also like some work that's ongoing and upcoming. So, of course, tropical cyclones, especially in the United States, but everywhere in the sort of tropics, we sort of know them as, just sort of um, packages of destruction and with high winds, low pressure systems which bring rain, flash flooding. And a really good example here is last year with Helene and Milton in the United States. And so we can see here, just grabs from the New York Times which show the sort of physical destruction, but of course the public health impact and the impact on people's lives and well-being is obviously sort of indirect and direct consequence of this, both in the short and long term. Uh, and so, one way of looking at the impact of tropical cyclones is to look at sort of excess deaths and how many people died on top of what we would have normally expected in those circumstances. And so, just a recent paper from Science Advances a couple of years ago, where we sort of tried to look at this by year and just taken a really good sort of an unfortunate example year of about 20 years ago now, 20-year anniversary of Hurricane Katrina, and we can see down here that there's the sort of Louisiana and the New Orleans area where there were sort of hundreds and then thousands of excess deaths estimated by our reckoning and by others over the past 20 years, and sort of as a direct and indirect result of cyclones, particularly Hurricane Katrina. But also, we could see in all the areas where cyclones hit in 2005, the sort of chance that there was an excess death. So these are absolute deaths, and these were sort of chances that the death count was larger than we expected during those times. And if we sort of wanted to look at that by, say, particular named hurricanes and by state, we can see by this figure from the paper that, recent years, we can see Katrina pop out, Sandy pop out in New York and New Jersey, Irma, Rita, just for some sort of highlights that stand out. One of the key things we sort of found was actually in the black boxes, a sort of second half of our study, that there were more excess deaths in that black box than the first half of the study. So going from 88 to 2019, the second half had more activity, obviously more population, and more excess deaths by our reckoning in this study. So while there are massive leaps in technology to stop hurricanes and typhoons causing damage, then of course, they are getting stronger under climate change and potentially reaching the limit of both the way we can communicate and the way that we can mitigate mortality too. And just another sort of highlight from that paper, unfortunately, that if we regress the excess deaths or just plot the excess deaths against vulnerability as measured by minoritized status in the United States, we found that the vast majority of the excess deaths were over 90% were in the top tertile, the top third. So of course, hurricanes and typhoons and tropical cyclones are stochastic random events. That their impacts are certainly not distributed evenly across population, including race, and so there is a structural issue there with regards to disasters in the United States and of course worldwide. So people die of different things after cyclones, and of course, you may sort of think the obvious ones being injuries, of course. So like people drown in the aftermath or get hit by debris. But really, this sort of recent paper from a couple of years ago was really highlighting how there are potential other sort of more chronic indirect impacts in the 6 months after cyclone. So cardiovascular diseases, infectious parasitic diseases, neuropsychiatric conditions, and respiratory diseases certainly had a signal in the association in that certainly the strongest tropical cyclones, otherwise known as hurricanes or typhoons. And of course, that's path dependent. So in the way that, this paper earlier this year by a postdoc worked with Tori Lynch, the kinds of floods that people will experience if there's tropical cyclone originating can have distinct pathways and sort of preparation depending on the nature of the flood. Of course, flooding is flooding in the sense that there's a body of water, but both the dynamics of the flood and the sort of warning systems behind the floods can play with the dynamics of the core specific outcomes there. So it's important to consider, the sort of hazards, that the panoply of hazards that tropical cyclones bring. But of course, people don't necessarily die from cyclones. So just a recent study of Medicare that we looked at, as sort of expected with hospitalizations and hospital visits for the 65 and over population in the United States in recent decades. Typically, what we see is a sort of decrease in the sort of immediate aftermath of a cyclone, followed by an increase. That sort of typology is for most of these outcomes, and I won't go into detail because I don't have time. That's except for maybe respiratory diseases and injuries. And so what you can see there is sort of this distinct sort of mechanism of decreased visits followed by increase. And then that's the exception with respiratory and injuries. So of course you may say, well, that doesn't mean necessarily that decreases in hospitalizations are good for you. And of course it doesn't. And so in this case, we looked at emergency dichotomized from not emergency. And so, the not emergencies were being were driving decreases. And the emergencies were driving increases. So, of course, from a sort of emergency planning perspective, there's going to be sort of increased on average, say respiratory diseases for hospital visits and for injuries, but elective and planned disrupted appointments are going to be decreased, and of course that has longer term implications for health after disasters, and in this case tropical cyclones like hurricanes. But so we've talked about the sort of short to mid-term impacts of mortality and morbidity, but of course cyclones. A recent study which I actually wasn't involved with, but was out last year, that I thought was really effective in demonstrating this, that they can cast a very long shadow, and this just as a highlight, the mortality here. You could see that the signal was estimated to last in the United States of elevated death rates for more than 10 years after cyclones, and to particularly impact the younger, very, very young, and in accordance with what we found was the excess deaths for black versus white in the United States was much higher too. And so and then the final sort of idea really with climate change is that places which are used to cyclones, yes, they have regular impacts like Florida, but places which have lower average impact and their exposure is increasing as a result of climate change, they are sort of historically underprepared, and so those cumulative impacts are sort of greater. And of course, that's relevant to the way that people evacuate. And Helen and Milton was an unfortunate example of how the dynamics of evacuation could play into the way that health impacts play out. And of course, with Helen, what we saw is really bad impacts in sort of the sort of central Midwest of the country, like North Carolina, and sort of West Virginia, or maybe more the South, if you like. And so we could see the path here, and that was what we found with using evacuation dynamics and evacuation data, is that Helen had a really bad impact because people didn't evacuate, partly, and also because it was impacting places which are historically not necessarily used to it. Milton, okay, you could see the path here. Across Florida, Florida was historically much more used to it, and also people evacuated. And so you can, if you're interested, I would look up that study. And as a highlight, we worked with Washington Post to create a data story, which you could see from the QR code there if you're interested, which I think, really hits home, like using plastic shoe leather reporting to create a data story to demonstrate perhaps why that impact from Helene was much sort of stronger and unexpected. And of course, that speaks to climate change in the sense that the direct deaths, if you take this one sort of measure of direct deaths from cyclones, of course, I wanted to make the point that indirect deaths are arguably much greater in sort of the long term, which is much more of a structural effect. But in terms of the short term, in the sort of recent past, the past few years compared with before, this is a figure from Yale Climate Connections, we could see that the storm surge historically was a much bigger proportion of deaths, whereas freshwater flooding originating floods are causing deaths in the recent past in the United States. Now, of course, there's different factors playing into this, but the general picture is that these are more coastal deaths and these are more inland deaths. And so the idea of cyclones getting stronger, reaching more inland, reaching areas which are historically less used to it, less resilient, I think that sort of speaks to the climate change element there, where there's sort of ticking time bomb of people not necessarily prepared and are going to be much more impacted in the near future. And as we've seen last year, though not this year yet, that's occurred. But of course, I've just talked about the United States, and so like recent sort of commentary I sort of put out with a Filipino colleague, Dr. Renzo Guinto, is really, of course, the sort of classic epidemiological issue is, we go where there's data, right? So radical progress in my field means accurately quantifying climate change impacts worldwide, not just where it's easiest to look. And of course, the US is where it's easiest to look. So I to pivot to sort of worldwide, both certainly from an exposure point of view now. And so, just looking at the last year's tropical cyclone season worldwide, we can see, that there is a lot of activity. There was a lot of activity. You can see the storm tracks there for each cyclone worldwide. But of course, areas in Asia and Africa and South Asia, East Asia, Australasia have a lot of cyclone impact. And if we sort of take the US in context, then for cyclones and so this is all cyclones, so greater than 34 knots, and this is hurricanes, typhoons, so the very strongest category 1 and above. We see, worldwide, and this is in the historical context from 1980 to now, where all those purple dots are 1980 to now, with the red dot being 2024. So we could see, as a sort of person day exposure, China, the Philippines, India, Bangladesh, Taiwan are all above the United States. United States is up there, but it's also not necessarily the highest. But historically, also, we're sort of on the higher end of things from last year. We're going to be probably on the lower end of things in the Atlantic basin in the United States. But global context, Western Pacific dominates, Southeast Asia. And for the very strongest, we see that countries and territories like Taiwan, Vietnam, Philippines are dominating. Though of course, United States is still up there in terms of the strongest. So we do worry about it for a valid reason in the United States. And just taking this in terms, regressing those person day exposures or just plotting them against deprivation index worldwide, we can see that a few things stand out, where these African areas here, which are Madagascar largely in southeast Africa, we can see high deprivation, high exposure relative to the rest of the world, which is a great area of concern for health impacts. So I just wanted to highlight that. And to put Helene and Milton, which we're probably most familiar with in the US from last year, in context, we can see that for the strongest hurricanes and typhoons, let's see. So yeah, Milton was fourth in terms of exposure to population person day exposure or population exposure just by single typhoon and hurricane. But of course, there are other places in the world which had much more estimated exposure. Now, of course, the health impacts are downstream of that, both in the short to long term. But I just wanted to illustrate how important it is for us to think about this in a global perspective. And in terms of the Philippines, a country which I have historical ties with, it comes top, the single biggest in Luzon in the north of the Philippines, was globally most exposed in terms of people exposure from this typhoon here, Taraji. And so it's really important, I think, to sort of think about that in the global context. But of course, those are sort of just disaster perspectives. And of course, we talked about this over time, but it's important to think about this in terms of climate change, because of course that's what we're here to talk about. So we know that from the IPCC, and scientists and atmospheric scientists all over the world are really thinking about this. And cyclones are getting stronger, which is no surprise from a physical basis, because the water's getting warmer, warmer air holding more water. The classic Carnot engine of a hurricane is more warmer water source acts as fuel for hurricanes and typhoons. So they're getting stronger, not necessarily getting more common, but getting stronger. And so that will play into how people are exposed, and of course the resilience interplays with that exposure and the recovery too. But it's not just the fact that cyclones are getting stronger. It's of course that people are moving into more cyclone prone and flood prone regions, both as a result of development and the fact that there is pressure to sort of move into places where people are buying houses. So this is a good example of in Wilmington, North Carolina, along Cape Fear River, where people are, just a snapshot from 2017 compared with 2023. And for example, in Vietnam in 2001 compared with 2021, we could see that there's a lot more development along potential flood vulnerable area. And so, of course, the question becomes, what is the global change in risk to that kind of exposure over time? And so, something underway we're looking at really is like when you take the very strongest category 5 cyclones, the person day exposure on average, the Philippines has a dubious honor of winning both in 1980 and in 2020. So over the recent past, change. But of course, there are changes. And the United States is high up there, but really this is dominated by the Asian countries here in terms of the basin. Um, and so the category 5 picture, which is the very strongest, remember, compared with the category 1 picture, is also interesting and distinct when you look at this from a city-based perspective as the sort of change element of things. And so working with colleagues at Imperial, we're sort of looking at whether or not, if we take, say, Asia, the category 1 change, the increase in exposure is much more biased towards the fact that there's population development. Whereas if you compare this with, say, category 5, the tail end of things, it does seem much more in balance between population and climate driven, where the unit of this is cities worldwide. And so when we look at the sort of change due to climate compared with the change due to population, there is much more of a climate driven component for the category 5, which are in dark, and that sort of plays out to various degrees in different basins and continents. So of course, then taking any one, I just wanted to illustrate the point of taking any one point, and this was a great report by World Weather Attribution and colleagues at Imperial and Grantham Institute, really where you can now take sort of the technology to take one typhoon, and perhaps Antonio will talk about this in terms of temperature, but to take one typhoon and then calculate based on what actually happened as a recent typhoon, Regasa, and look at the return periods under different scenarios and what we would have expected the impacts to be from the speed. And so looking at this and translating it to a specific health impact is obviously the next step, and one in which I'm super interested in, and hopefully you are all interested in. And of course, what we're showing, what they showed here from the IRIS model, which was the basis of the previous slides, is that it went from a weak category 3 typhoon to sort of strong category 3, and so under climate change, that typhoon was about 50% more likely. And so, the idea of the typhoons and hurricanes having health impacts, I hope that I've sort of shown you that is both a short-term and a long-term phenomenon. But in terms of the change element too, and in terms of the attribution element, there is a sort of key science and key learning which I'm very excited about being involved in. And this was a recent so I guess a white paper by Wellcome Trust, and looking at the ways that we sort of think about climate change attributable deaths, of course, or attributable impacts. So a lot of climate change and health, frankly, is weather and health, and so that's fine. But in terms of the climate change element of things, of course, we need to understand how we attribute the change, or the footprint of climate change on top of what was happening. And so, of course, if there's a heat wave, that there are typically going to be some bad impacts from that, but what is the extra impact? And so there's some really good work going on in that. But in terms of cyclones, this is sort of all the pieces being put together. I think is really exciting. And so, I sort of formed this nascent geotropic network, and I invite you all to sort of register your interest if you are interested. And so, like, I sort of, as you could see from 2024, that was an example of our global data set. And so we're looking at different countries, working with different colleagues, and really just a global community of resilience, which I think is super important. Particularly, I think historically, epidemiology and public health has been a sort of global north to south thing, but there is so much in the global south, particularly with tropical cyclones, that I think we can learn. Um, and they deal with this in a sort of, it's so ingrained, for example, in the Philippines as a political component. How do you deal with disaster? They talk about it every time there's an election. I don't remember in the US, certainly last election and the election before and the election before that, okay, there were other things to talk about. Well, I don't remember really. We're talking about how we deal with disasters and how we deal with FEMA. And we're seeing the sort of repercussions of that politically now, of course, but that really is a key component of how we deal with this. And of course, just sort of wrapping up a little bit, there is frontline resilience from hurricanes, and that really comes from how healthcare resilience is dealt with and how dynamic that is in a disaster environment. So I just wanted to sort of shout out this. I consulted with the AmeriCares and Harvard School of Public Health with dealing with hurricanes as a sort of frontline component. And that was with my friend Nate Matthews Trigg, and I just wanted to just briefly highlight, as a non sort of not totally related, but I think our solutions for resilience will come from many different sources. And so thinking outside of academia, just trying to think about the way that we sort of come up with solutions and view solutions and respect the public. We set up this heat prep forum, and on Reddit, if that means anything to you, you can see the QR code here. There's just me and Nate, and it's turned into the largest public heat forum in the world. And so you can see some recent studies by friends and colleagues at Imperial there. But the beauty of it is that it's decided by the community. And so these are some recent high impact posts. USPS carrier dies due to heat waves. I didn't see that in the popular press. And then some more sort of fun, in inverted commas, still someone trying to create the still suit there from. But so it's a really rich source of how people are dealing with things. So watch this space, and I invite you to go and look at heat prep if you're around. Just wanted to say thank you to being able to go around for the past couple of years, sort of talking about cyclones a lot worldwide. Just if you're interested, I work with my friend Gary Falos Akis, who works a lot on climate change and health too. We've got a training in 2026, now a 3-day workshop by popular demand in next summer in New York. And last, I just want to say, now with all of this work, it's sort of really a team science thing. So I just wanted to list the members of the lab and the highlights of people working, because really, I'm just sort of trying to raise up my team's work. So I just wanted to say thank you to them. And of course, thank you to ISEE North America. And so that's concludes the talk. Thank you.
Thank you so much, Robbie. That was great to hear more about your work. And then next we have Dr. Antonio Gasparrini, who's a professor at the biostatistics at the London School of Tropical Medicine and Hygiene. And I will pass it over to you. Thank you so much.
Thanks, everybody. Well, thanks to the organizers, especially for inviting me. Really glad to be here. I'll try to share my screen now and to put everything in full screen. I hope you can see it. Now,
this is not the full screen. Sorry, there it
is it fine?
Yes, now it's the full screen. Thanks.
Okay, excellent. And possibly, I don't know if I can do it quickly, but just give me 1 minute. Okay, let's have a start. Now, regarding the topic, I was, suggested between a methodological and an applied, let's say, presentation to go for the latter, but I couldn't help myself. So I will present results from a series of studies on temperature-related mortality and climate change in Europe, but of course I chose a methodological angle for all of that. Now, the aim of these studies was to investigate mortality risk for non-optimal temperatures and also produce some climate change projections across Europe. We could have easily done it the usual way we do it. I mean, we have a bunch of cities available in our MCC, multi-country, multi-city collaboration database. And we have a two-stage framework we have already established for doing that. But we wanted to, in a way, to progress further, especially addressing some of the limitations of this framework, which is mostly that, of course, all the analysis refers to a selection of locations, mostly cities, in this case, in Europe, and therefore doesn't cover the whole population. And in addition, of course, we don't take into account many other issues, just like the age differences between cities and how the impacts can be different by age, and there were other methodological limitations that we wanted to address. So we wanted to extend the analysis to all the 854 urban areas in Europe, which are all the cities with more than 50,000 inhabitants, with the problem that, of course, we don't have data for all of them. We could get some data, which is not mortality data, for us, for all these countries, from a database from Eurostat, but of course we don't have the related exposure response relationship between temperature and mortality to be able to measure the impact. So how we did it, basically we collected some data. I already mentioned the MCC database. We had data for 232 cities out of the 854 for a period between 1990 and 2019. We collected historical data from the Copernicus database, which actually covers the whole world, so we could get this data for anywhere in Europe. We had projections of temperature for the NASA Next GTBP database, which offered data on 19 climate models, all of them bias corrected based on CNIP6 output, therefore the last generation of, let's say, climate models. In addition, we collected other environmental variables, just like pollution or green space from other sources. And in particular, very importantly, we could collect an harmonized database of city-specific information on demographic, socioeconomic, topographical characteristics, all harmonized in this urban database of 854 cities. Now, regarding the modeling, of course, we have an established model for time series analysis we developed together with others. Don't bother you with the specific algebraic details of the specific of it, but of course, it's an established time series model. The difference in this case was that we were running the model at different age groups in each city, possibly different age groups in each city. Of course, we could rely on the usual methodological harmony that we already developed, in particular, applying distributed lag nonlinear models to model complex exposure-lag response risk surfaces across all the cities, accumulating all of that in so-called cumulative exposure response curves that you can see on the right, And this curve gives an idea about what is the increase in risk for both the cold part of the temperature range, which is the blue, or the hot part, basically heat, but also interestingly, what is the point of the minimum, which we call minimum mortality temperature, and it represents more or less the optimal temperature in each location. Now, the real extensions are actually in the second stage meta-analysis that we usually apply basically after we have run all these analyses in the first stage for all the cities. We pooled all this information in the second stage. And this second stage meta-regression is slightly different than usual because basically we take the coefficients of the spline modeling, this exposure response relationship, we model all together, but including a series of meta predictors, and I will list them in a moment, but also some kind of residual random, let's say, variations that can also be spatially structured, basically. So these are the two components of the model. The first component, which is the fixed effects, are very important because in there we included both continuous age terms, basically to model continuously what is the effect of age in let's say, modifying the exposure responses, but also what we call composite vulnerability indices, basically how this shape changes from one city to another depending on the characteristics of the city itself. So this allowed us to model, first of all, from a single model, differential age effects, and this is the representation of the so-called pooled exposure response relationships, showing that the effects of both heat and cold tends to be much higher for with age, and therefore for the elderly, and with different shapes between them. And actually, if we look specifically at the point of minimum, we can see that this point changes quite a lot with age and tends to increase with age in terms of the percentile of temperature, going from the around the 50 percentiles, basically the median temperature at a very young age, but increasing up to the 90th percentiles on average, of course, across Europe at a very older ages, let's say. Now, in addition to this, the other important part of the model is about the so-called vulnerability drivers. Basically, we collected a lot of information from all the cities from this standardized database from Eurostat, including demographic, for example, total population life expectancy, or socioeconomic, GDP, unemployment, education, and others, but also characteristics of the city, just like imperviousness, tree cover, grassland, green space, and also other important environmental characteristics, just like greenness or exposure, average exposure to various pollutants and others. Basically, the problem of this is that these are too many to be able to model all together in a second stage meta-analysis. So what we did, we applied the partial least square reduction, basically taking what we call forming vulnerability scores, which are combinations of these characteristics, identifying in a way composite indices that can identify differences across exposure responses curves in different places. And this is quite interesting because it shows that this model with this composite is able to capture fine differentials in a way across cities. So for example, in this plot, you can see in red dashed line the original first stage estimation for this specific age, which actually can be quite uncertain and unstable because, of course, there are not many deaths for that specific age group in that specific city. And then the other curves are the models in which we increase the number of vulnerability components we include in them. And you see that these increasing curve tends to make the exposure response more similar in some situations to the original first stage curve. And in particular, the model with the 5 components can capture these seemingly higher effect of heat, which cannot be captured by simpler models. So basically, this idea of including composite indices based on many different characteristics of the city can capture fine differential in risks across cities themselves. Now, another interesting part was the fact that from this model, there's also a random component. Basically, there is some differences across cities for which we cannot easily understand variations, basically. This can be captured to these best linear unbiased predictions that are computed with that. But of course, we wanted to see how much these original predictions differ from the prediction from the model only based on the fixed effects, which is the part that the model can capture directly and the part that is not captured, and there's a residual variation. And we can see that especially for heat, there was still a substantial, let's say, residual heterogeneity we couldn't capture. So what we did, we applied that so-called multivariate rigging in order to capture local differences in curves, and we were able to spatialize these residual risks for all the coefficients of the splines across the whole space of U. So this is the way in which we can, both with the prediction from the model and the specialization of risk, derive exposure responses for all the cities in our database, even if we don't have data for probably the majority of them. Through this, we could compute the exposure response relationship and specific effect summaries, just like effects for the first and 99 percentiles for all the cities, representing basically summaries of the effect of heat and cold, showing that these varies dramatically across cities, both within and between different parts of Europe. And from here, of course, we can also compute the full age-specific mortality rates in terms of excess mortality. And also this one, you can see that it changes dramatically between different parts of the city of Europe. Not unexpectedly, heat seems to be much more important in Southern Europe if compared to Northern Europe in terms of excess mortality, while cold varies in slightly different ways, and in particular seems to be very low in the western part of Europe compared to all the other parts. Now, another thing that I will probably just mention quickly is a relatively technical detail about how we compute uncertainty around all of these. And the way we have computed uncertainty so far in the two-stage model that we have applied also with MCC is slightly biased, because for the fact that the best linear unbiased predictions that we use for computing the risk in each city they are not independent. So when we aggregate the risk, the impacts in terms of excess mortality across regions, countries, etc., we need to take into account these additional correlation between the estimates. So we are producing in a methodological article that I will present later, a different methodology that can account for this additional uncertainty. And this graph shows for few specific cities, in particular in Italy, how including a different sampling for the Monte Carlo iterations that we use for computing uncertainty can account for this additional, let's say, uncertainty that otherwise will be underestimated. Now, from all these analyses, we were then able to produce mapping in a way of impacts and features of the relationship with temperatures for all the cities that we have in our database. And although, I stress again, we were starting from a set of 232 cities, we're able now to derive exposure responses for all the 854 cities, and for all these cities to compute different extract, in a way, different summaries. In particular, we're interested not just in the impact of the heat and cold, but also in this case for mapping the so-called optimum temperatures or minimum mortality temperatures. And these two graphs shows these minimum mortality temperatures in a temperature scale, or the so-called percentile scale, showing again extreme differences across Europe. Of course, on a absolute scale, the minimum mortality temperature seems to be higher in hotter countries, just like southern countries, just like Spain, Italy, or Greece, and of course being lower, below, let's say, 17 degrees for northern countries. But also you can see that there is a huge variation also between countries. For example, you can see that in Italy, places closer to the coast tend to have a higher minimum mortality temperature if compared to the central part. Or in Spain, you can see places in colder places, in colder regions, in north of Spain tends to be a much colder minimum mortality temperature if compared to others. Of course, everything reverses if you think about minimum mortality percentiles. So in terms of percentile of temperature, the percentile is much lower in southern regions if compared to northern regions. And the comparison of these two can be indicative in a way of a sort of adaptation of the population to the local climate, which is, but this adaptation is partial. So in absolute terms, of course, hotter regions, they tend to have a higher temperature, minimum mortality temperature, but in relative scale, colder regions seems to have a higher percentile. Of course, even more interesting is the comparison of the impacts of cold and heat that we represent in here. And even here, you can see a differential patterns of impacts. So in terms of cold, we can see that northern regions, but especially Eastern Europe, seems to be very much affected with a higher standardized rates for excess mortality due to cold, but also, of course, there are larger regional differences. For heat, of course, the pattern is completely different, but there are some similarities. So heat Eastern Europe still very much affected, while, for example, Southern Europe is also showing very high standardized excess death rate due to, of course, heat. Now, after this study, we were planning, of course, to do additional study looking at the projections of impacts in the future. And in order to do that, we did it in a slightly different way. So we published basically all the code and data of these initial studies on historical relationships, let's say, in a respective GitHub and Zenodo repository. And the Zenodo repository is particularly important because it stores all the exposure-response relationships and the related impacts together with ways to get uncertainty measures for all of them, for all the 854 cities in Europe. So what we did for the, let's say, following studies looking at the impact, well, the projected impact on the climate change, instead of rerunning everything, we rely completely on this data from the Zenodo repository, and we use the exposure responses for projecting the risks in the future under different climate change scenarios. So we'll go back to this later, but of course we run these studies in which we look at the effect of both heat and cold under different scenarios across the whole Europe. And this graph shows some interesting results about a very specific summary, which is this so-called net effect, which is basically the net sum, if you want, between the increasing what you expect in heat-related mortality because of climate change and the temperature is becoming hotter, and the decreasing cold-related mortality because of the same reason. Now, this idea of the net effect has been used quite a lot to, well, I would say dismiss health effects of climate change related to temperature under the assumption that, well, cold-related mortality is much more important in terms of absolute impact. That, of course, any change in the future in an increase in heat-related mortality will be completely, in a way, offset by the reduction in code. Actually, we found that this is not quite the case, and on average across Europe, actually, we see that there is an increase in this net effect across the century under the three different SSPs, RCPs scenarios, basically incremental changes in climate in the future, going from a more moderate to very extreme change. And we can say that especially in the extreme change, in particular in the region of South and Eastern Europe, the net effect will be massive and absurd. And we can look at the map under different scenarios, which is for specific temperature increases, average mean temperature, global temperature, from 1 to 0.5 to 4, we see that even under the mild, very mild, 1.5 increase, in Southern Europe, there is already a positive net effect, but that this will become more dramatic under more extreme climate change scenarios, and in particular, these positive net effect will become positive also for many other regions in Italy, apart from the very northern part of the continent. Now, first of all, to wrap up, I presented here a set of modeling extensions for this two-stage framework, and we applied in analysis on Europe. And you can see that the interesting parts of this, the definition of composite vulnerability indices, the extrapolation of risk functions, that is, you can map basically entire areas, even if you don't have the data for all of them. And of course, there are directions for future developments for all these approaches, including, for example, and of course, my co-presenter here would be very interested in seeing Bayesian applications of all of these, of course. And of course, the framework can be extended to other relevant outcomes. Now, I finish presenting, first of all, published works, acknowledging that all of this has been led by my colleague, Pierre Masselot from the Environment and Health Modeling Lab at LSHTM. So there's a first methodological article with a tutorial, including R code, replicable code, that I will invite you to look at, and two published analyses on the historical and climate change future impacts data. Finally, some links and references, first of all, to the Environment and Health Modeling Lab, but also for this case study, there are the complete code and especially all the data, and there's another repository that each of you can reuse to do health impact assessments in Europe using the published exposure responses relationships plus other material. So I thank you for the attention, and again, the organizers for having invited me, and I hopefully stop my presentation here. Thank you very much.
Thank you so much to both of you. And we have some time for questions. If anyone has any questions, please feel free to put it in the chat or use the raise hand feature. Thank you all so much for your presentations. Okay, I'll go ahead and get us started. I have a question for Robbie. And Robbie, you had mentioned at the end of your talk that particularly in the US, that there hasn't been a lot of discussion regarding any policy changes in any of the recent elections. And I'm wondering if you could speak a little bit about what sort of policy changes you are thinking that might help mitigate some of the impacts of cyclone exposure, and maybe how that's been implemented in other parts of the world.
Right. Yeah. So, I mean, to be honest, obviously there's been other concerns in recent American elections. So, without sort of getting into the weeds of that, there's understandably a crowded market of discussion from what people would be talking about in elections in recent times in the US, both in terms of, fundamentals of democracy and other things, of course. But in terms of what I was sort of referring to, I was really referring to sort of the sort of long-term stability and solvency and effectiveness of things like FEMA, and the way that the recovery finances has been sort of biased differentially towards richer, whiter families and households to recover insurance. It's biased towards health homeowners, for example, and it's sort of biased towards certain states as well. And so, in terms of the learnings from other countries, first of all, just to really regard the fact that, just talking to my Filipino colleagues, really thinking about how disasters are sort of part and parcel of the way that they would have an election platform on, say, a FEMA equivalent in those countries, and they would really be part of the debate and discussion. And of course, you may say, well, of course, it's a different circumstance in other countries, low and middle income countries, but really my response would be, there are impacts here, both from weather and potentially from climate and climate change that will rival those in other countries. And so just really sort of recommending that it becomes, and this is sort of from a grassroots perspective as well as from a political perspective, that they become discussions from a financial perspective, or both a community perspective, for example, community-led solutions, minimizing isolation of older adults and things like that. All of those in terms of action plans, disaster resilience, I think we can learn a lot from other places.
Great, thank you so much. Do we have any other questions? Yes, I see that if you've got your hand raised, you can go ahead and unmute yourself.
Are you hearing me?
Yeah.
Okay, thank you. My name is Jalan from Australia. I would like to appreciate both presenters for the very interesting presentation. My question is for Prof. Antonio Gasparrini. My question is, how can we really consider the spatial dependency or the correlation on the analysis, what you already presented? Sometimes it's very confusing to consider both the time dependency and then the spatial autocorrelation, because by nature, the environmental variables, whether temperature or air pollution or whatever, they are more likely to be correlated spatially because they share so many common characteristics based on specific geography. So do you have maybe any idea just to consider simultaneously with the temporal pattern of the environmental factors with their geographical dependency? Thank you.
Oh, well, thanks for the question. It's an interesting one. Yes, of course. Basically, the model as I presented includes both a series of composite indices of, we call it composite indices of vulnerability, basically combinations of variables that are measurable for all the cities. And these, of course, are spatially correlated in itself. So if you look at these derived composite indices, you can see in the map that they are very much correlated in space. And through this, the model is already able to capture a lot of the spatial variation in the exposure responses. Actually, most of it, I would say. There is, however, as an example, if some areas are more polluted than others, and if pollution, understandably, can modify the effect of temperature and therefore making people more susceptible in a way to health effect of temperature, this will be captured by the model because we directly measure air pollution in that space. And air pollution is part of these composite indices, and we are able to capture this effect in the model. There is, however, a residual part of spatial structure, spatial differences in a way across the exposure response that we cannot capture. And these were the second part of the model, which is this spatial kriging. And of course, you can model this also with in other ways. But is the idea that you can capture the spatial structure on these differences and add it to the model in a way, modeling this residual variation in a spatializing it. Now, through these two components, you are then able to predict an exposure response in a city, because for this city, we know the characteristics of the city, so we are able to predict specific fixed effects. And in addition, we can add from this spatial surface, residual surface, the specific deviations that is can be assigned to that city. Now, the model is not perfect because ideally you would like to capture the entire spatial variability with a fixed effect, is something you can directly model. But of course, this is not possible, and we apply this method, and I'm sure there can be interesting extension also and improvement from this method. I hope I answered your question.
Yes, I got it. Thank you very much.
Do we have any other questions? Yes, I see one in the chat. Antonio, this question is for you. Do you want me to read it out loud, or can you read it?
Well, I can read it. Well, the question is about regarding the US hospitalization data for 20 years. If you apply two-stage model, the data volume within each zone might be too limited to support stable DLNM estimation. Your opinion, approximately how much data would be needed to obtain relatively robust results? And do you think would be appropriate to set a threshold for inclusion? Well, first of all, yes. There is this problem that you should have enough data in each space in each area for getting a relatively stable estimate, maybe uncertain but stable estimate. Of course, there are now methods to address this. I mentioned three. One is the method that we developed is called case time series, in which you combine in the same model multiple small areas in a single model, potentially for including measurable differences between them. And there is a paper in 2022 in Lancet Planetary Health under my name as a first author, showing how to do it and a tutorial. There are other methods now implemented DLNM in a Bayesian version that can run a single model accounting for these differences. And there is some papers already from the group of IS Global and also other people, including Gary Fallos, Konstantinidis, that Robbie mentioned that they're working on this area. The third one is a method we are working on at the moment, and it's about constrained estimation, and in a way exploiting some assumptions you can make on the shape of the function in order to have more stable estimates, even when you have very limited data. So I mentioned these three. The third one is under development, but the first two are already published and available for you.
Thank you so much. And I think we'll need to end here because we're actually just over time. But thank you so much to both of you for your presentations. I really learned a lot. And we're also going to be posting the recording for this on the ISE channel. So thank you so much.
Thank you very much.